Hello and welcome to my YouTube channel. Today I will present an article, Global Warming. Developed by Christian Prajura. Is global warming real, or is it just a story imposed on us by the world occult? How much is true of everything they say on the internet? Are summers warmer? And most importantly, is man guilty of all this, or is it all part of the Earth's natural processes? In the next series, I will try to shed light on the global warming process and I'll leave you to draw your own conclusions, including mine. I'm going to divide the series into 3 episodes, one after the other. In the first episode, today's episode, I will discuss carbon. Is there really too much of it in the atmosphere? Who put it there? In the second episode, we discuss the phenomenon of atmospheric warming. Right. Is warmer, and why is this happening? You mean we have global warming? In the third episode, one will talk about the consequences of global warming and the measures needed. This will undoubtedly be the most controversial. In all these episodes, I will approach the topics using the scientific approach, as I have been educated, and with all my sincerity. Sincerity is, in fact, part of the scientific method. Let's kick it off with the first episode. About carbon dioxide in the atmosphere. Is it too much, as we are told? Is man responsible for this excess? Carbon dioxide. The biosphere on Earth is a balance between all its components: bacteria, plants, animals, oxygen, and carbon dioxide. We know that animals absorb oxygen and release carbon dioxide, and plants the other way round, they absorb carbon dioxide and release oxygen. In this way, the Earth breathes from year to year. Plants grow from spring onwards and extract carbon dioxide from the atmosphere. Its concentration should be low in autumn, when the trees wither. In winter, until spring comes again, the concentration of carbon dioxide in the atmosphere rises again, recovering. This is what we see in this graph. On the horizontal axis are the years, and on the vertical axis, carbon dioxide concentration. We can see that the concentration is lowest in autumn, towards the end of the year, and highest in spring, when plants, flowers, and trees come back to life and the human soul seems happier with so much greenery around. Science works. On the left axis, we see the concentration of carbon dioxide in the atmosphere, about 400 ppm, i.e. 400 parts per million inch. This means that if we take a volume of dry air containing 1 million molecules, in total, oxygen, nitrogen, etc., 400 of these will be carbon dioxide. That's 0.04% of the molecules. The atmosphere has a total mass of about 5.5 million billion tons. Molecules have different masses. If we want to know the total quantities, we need to use the following conversion. 1 ppm of carbon dioxide is equivalent, using the mass of molecules, to a mass of about 7.8 billion tons, i.e. 7.8 gigatons, of carbon dioxide into the atmosphere. The carbon dioxide molecule has 1 carbon atom and 2 oxygen atoms. Of the 7.8 gigatons of carbon dioxide, the mass of carbon atoms alone will be about 2.1 gigatons. Next, in this video, we will only look at the mass of carbon atoms in carbon dioxide. For example, if we want to know the total mass of carbon atoms in the atmosphere, which come from of carbon dioxide, multiply 400 ppm by 2.1 gigatons, giving about 840 gigatons of carbon. These measurements were first made by Charles Keeling in the 1960s in Hawaii. To his surprise, he also noticed something else: the carbon dioxide concentration increases over time. Let us take another look at our graph. Here we see an average increase of about 2 ppm/year. Using the conversion, we get that the atmosphere is being charged with an extra 4 billion tons of carbon every year. Surprised too, Keeling continued his measurements in Hawaii. Here's what they look like so far. We see how, since the 1960s, growth has been steady, even slightly accelerated. Carbon dioxide concentration increased from 310 ppm to 410 ppm. That's about a third. This is the moment when we should be surprised. A third? How can the concentration of carbon dioxide increase by 1/3 in just 50 years? Could this be a natural process? Is it something we have done in the meantime? For that, we need to look back in history. But how can we do it? For that, until the 1960s, no one measured the concentration of carbon dioxide in atmosphere, and 100 years ago, there were no machines to measure it. Hey, this is where science comes in. And Antarctica, which is not an insurmountable barrier, as flat Earth advocates claim. Well, in Antarctica, scientists are reaching and drill ice. And what do you know, year after year, a new layer of snow settles on top of the old. Have you seen how we can measure how old the tree is by looking at its circles, because each one grows in a year? The same goes for ice, in every sample. The drilled hole that is brought to the surface, you can see the passage of years. What's more, each piece of ice is a time capsule. When the snow settles on the ground, it closes, in its small interstices, portions of the atmosphere that existed then. This is ideal for researchers. Unpack the sample taken from depth, calculate, from the surface, the years it represents, and then release the air there in a special meter. That way it directly measures the composition of the Earth's atmosphere in those years. Here's a result for carbon dioxide concentration. On the horizontal axis is time, from 1600 to today, and on the vertical axis, the carbon dioxide concentration. On the right-hand side are added data measured in Hawaii after 1960. What do we see? First, the two curves, from Antarctic ice and Hawaii, complement each other very well. That gives us confidence. The second thing is suspicious. 300 years ago, the concentration of carbon dioxide was about constant, and only in the last 200 years has it begun to grow at an accelerated rate. Let's look back some more. Here's what it looked like 10,000 years ago. And back then, the carbon dioxide concentration was constant. It has risen sharply only in the last 200 years. Further back? We've got samples in Antarctica that can pull samples from depths and where the snowpack is almost 1,000,000 years old. We have. Here's what the machines measured when they smelled the air at the time, freed from the ice that held it prisoner. Again, on the vertical axis is the carbon dioxide concentration, and on the horizontal axis is time, this time in thousands of years, starting 800,000 years ago. What do we see? Two things. 1. The concentration of carbon dioxide has varied over time, between 200 ppm and 270 ppm, over a period of 1,000,000 years. 2. In the last 200 years, it has risen sharply, exceeding 400 ppm. Here you can see very clearly. Well, how the growth is sudden, almost instantaneous at this scale of hundreds of thousands of years, the line is almost vertical. Now it's time to take a breath and draw a first conclusion. I say my conclusion. The sudden increase in carbon dioxide over the last 200 years must be man-made. See how the rise on the right side appears almost like a vertical line, so sudden is it? It is unlikely that such an extremely sudden increase is natural. What could it be? And, if it were, why would it have appeared just now, when human civilization is experiencing a technological growth as sudden as the geological timescale? I don't see another answer. If we are honest with ourselves, we have to admit that man has done something that has destabilized the existing balance and led to a surge of carbon dioxide in the atmosphere. What could that be? Fortunately, by following the scientific method, the answer lies directly. Burning fossil fuels. But, I say, let's not just throw the answer on the table, like an all-knowing teacher would, but to see together why this is so, using the most powerful tool nature has given us, the brain. Let's think with our minds, I say. Industrial emissions of carbon dioxide. The starting point is also mentioned by Charles Keeling in his original works. Namely, that man burns wood for heat, coal to run his steam engines, oil to start the machines. That is, it burns fossil fuels. And the number of people has increased over the last few hundred years, and so has the amount of fossil fuels burned. Let's take it one step at a time. Have you seen what happens when we put a wood on the fire? After it burns, it seems to disappear completely. Only a little ash remains behind him. Where did the wood go? That only the laws of physics tell us that matter doesn't just suddenly disappear. How would a student want to disappear from an exam when they don't know? Well, the wood's gone up in the air. The hydrocarbons in wood, i.e. hydrogen and carbon, have reacted with oxygen in the air to form carbon dioxide and water. The carbon and water vapor then rise into the atmosphere, as shown in this sketch. And we wonder, does that make sense? How many families on Earth? A few billion? How much wood does a family use when winter comes? Say a few tons? About half of this is the mass of carbon atoms. We get that several billion tons of CO2 end up in the air every year. Of carbon, the calculation is very approximate. We are only interested in the order of magnitude. How much does the amount of carbon dioxide in the atmosphere increase each year? We've seen, over the last few years, by about 4 billion tons per year. That's the same order of magnitude. Let's not rush to conclusions, I say. Why? Because we need more precise data on emissions from fossil fuel combustion to get a good understanding of what is happening. Let's look here. On the horizontal axis is time in years, and on the vertically, the total amount of carbon dioxide emitted into the atmosphere by burning fossil fuels. We can trust this chart. It is made because the world's factories are now basically monitored for carbon dioxide emissions. It is known how many factories there are and how much carbon dioxide they emit from their chimneys. Only a worldwide conspiracy could falsify this graph, but today we're only talking a little bit about conspiracies. We see how billions of tons of carbon are emitted every year, as we simply estimated at. First, by burning wood. We're still seeing how the growth is pronounced in recent years, so let's add another graph. Here you see the same graph in red, only now the blue line, vertical axis on the right, is superimposed. A graph of the world's population. We see how carbon dioxide emissions correlate quite well with population growth. Well, from the graph we can also see how, in recent years, the amount of fuel has increased. Fossil burned per capita because, on average, development has increased. Now we can also verify our theory. In recent years we see that we are going up, by burning of fossil fuels, about 9 to 10 gigatons of carbon into the atmosphere every year. On the other hand, we have seen how the atmosphere has an annual growth of only 4 gigatons of carbon per year. That's a factor of 2 difference. How can that be? Did we get the calculations wrong? We're taking a break. We need to be honest with ourselves and with science. What's going on? If we put 9 to 10 gigatons of carbon in the atmosphere every year, how can the atmosphere accumulate only 4 gigatons of carbon per year? Does the rest go somewhere else? It's time to go into more detail. The ecosystem carbon dioxide. Earth was not so welcoming to life in the beginning. At first, its atmosphere was 30 times denser than it is today and made mostly of carbon dioxide. Carbon dioxide has been removed over time by 2 mechanisms: absorption by the oceans and its conversion to oxygen by cyanobacteria. Life, as we know it, has made its own place on this Earth, and without cyanobacteria, which transformed the planet's atmosphere, we wouldn't exist today. The annual variations in carbon dioxide concentration, which we have seen before, are proof that the biosphere is still breathing in the atmosphere it has created. Let's take a closer look at the carbon dioxide cycle on our planet. Let's look at the following graph, reconstructed for the period before the Industrial Revolution. We see how, at that time, the atmosphere contained about 600 gigatons of carbon. Every year, the biosphere would extract about 120 gigatons. The carbon dioxide used by plants, trees, etc., and put back 60 gigatons, the one exhaled by animals, for example. At the same time, half of the carbon dioxide sequestered by the biosphere goes into the soil through the death of plants and animals. In total, about 60 gigatons per year. From the ground, about 60 gigatons of carbon are also put directly in the atmosphere, e.g., through the breakdown of debris by certain bacteria and other microorganisms. Basically, the biosphere is in balance with the atmosphere. The same happens on the right side, where we have the contribution of the ocean. The ocean, surface and deep, stores about 40,000 gigatons of carbon. At the ocean surface, water interacts with the atmosphere in many ways. Some of the carbon dioxide is absorbed by the phytoplankton formed from aquatic plants. Another part dissolves partly in the water, as do other gases. Here, carbon dioxide can react with water molecules to form carbonic acid. In total, the ocean traps about 90 gigatons of carbon from the atmosphere each year. On the other hand, the ocean puts carbon dioxide into the atmosphere. Thus, at the end of their lives, the aquatic plants that form phytoplankton are decomposed by microorganisms and carbon dioxide is released, some of which ends up in the atmosphere. Another part of the atmospheric carbon dioxide, dissolved in water, is released back into the atmosphere. In total, 90 gigatons of carbon go up in atmosphere every year. And the ocean, like the biosphere, is in balance with the atmosphere. Interesting is what happens to the carbonic acid formed in the water. It interacts further in the ocean and forms substances called carbonates. These settle to the ocean floor. Of these, through the movement of tectonic plates, slightly less than 0.02 gigatons of carbon, exact figures are hard to come by, reach in the depths of the Earth every year. But elsewhere on Earth, by volcanic activity, induced by the movement of the same tectonic plates, still slightly less than 0.02 gigatons of carbon are released into the atmosphere per year. This closes the carbon cycle. The image above is the balance image. If not disturbed. Otherwise, carbon in the atmosphere is conserved constantly over millennia. Over longer periods of time, tens and hundreds of thousands of years, other mechanisms intervene to unbalance the situation. But we're just talking about what happens in these several hundred years of human technological evolution, combined with a population explosion. Imbalance atmosphere. What happens today, when mankind puts 9 to 10 gigatons of carbon into the atmosphere every year? As you see, only 4 gigatons of carbon remain there, the rest has to go somewhere else. But where? Well, the answer is the biosphere and the ocean. Roughly, a little less than half of the 6 gigaton difference is taken up by the biosphere and the other by the oceans. Basically, because of the excess carbon dioxide in some places. Vegetation in the world is multiplying, absorbing about 2 to 3 gigatons of carbon from the atmosphere. Another 3 gigatons go into the oceans annually via phytoplankton and other. In the end, about 4 gigatons remain and accumulate in the atmosphere. What do we infer from this? That the biosphere and the oceans help us, only even they can't keep up with the accelerating rate at which civilization is releasing carbon dioxide from fossil fuels. Now would have been the time to detail carbon dioxide emissions by country. I decided not to do that, because it leads into a political discussion and I want to keep this video to the scientific aspect of the issue. Maybe in the future, I thought it might be better at the end to address a few myths about carbon dioxide and then the conclusions. Myths about carbon dioxide. Carbon dioxide emissions are due to volcanoes, man has no significant contribution. False. We have already seen that emissions from volcanoes are about 0.03 gigatons of carbon per year, and man's is approaching 10 gigatons a year. Clearly, man beats volcano, as can be seen from this graph, which shows the evolution over time, with green is man's contribution, with purple putting the right color at the bottom. Volcanoes' contribution. The concentration of carbon dioxide has varied before, so what's happening now is natural. False. Let's look again at the chart in question. We see how, every 100,000 years or so, the concentration increases and then decreases. As we see in the next episode, this has to do with periods of glaciation, caused by the Earth's orbital motion. Mind you, the growth over the last couple of 100 years is much greater and, more importantly, much faster than the tens of thousands of years of variation so far. You mean there's something in addition, and that something can only be caused by man, as we saw above. Plants and trees need carbon dioxide and absorb all the excess due to human civilization through the burning of fossil fuels. False. I have seen that part of the statement is true. The ocean and plants absorb more than half of the amount emitted by humans from burning fossil fuels. But even they cannot cope with such a rapid rate of man-made emissions. Approximately 4 gigatons of carbon accumulate in the atmosphere year after year, not absorbed by plants or oceans. Conclusions. I don't know what you think after this foray, but I have been honest with myself and the science that I see on this channel. The bottom line for me is that man is indeed putting large amounts of carbon dioxide into the atmosphere, and year. Plants and oceans can't keep up with the pace imposed by humans and absorb only part of it. Next time we'll move on to the next episode. What are the consequences of this increase in carbon dioxide concentration in the atmosphere? Is the Earth's average temperature really rising? In other words, are we having global warming because of this? Until next time, please subscribe if you haven't already done so by clicking now this subscribe button. Thank you to those who support us on Patreon and here by becoming